Today we are diving into a really strange and beautiful mathematical object. One that might just hold a new language for meaning, and maybe, just maybe, a new blueprint for artificial intelligence.
So what is it? It's called the fractal of Senezi. And yeah, it looks incredibly complex, almost otherworldly. But here's the crazy part. It comes from something super simple, something you definitely learned back in elementary school.
And that really brings us to the big question we're going to tackle today. What if a simple times table, of all things, held a hidden map of meaning? A secret structure that could describe everything from philosophy all the way to the architecture of AI itself. It's a huge idea. To even begin to answer that, we've got to look inside the numbers themselves. Because hidden inside those multiplication tables we all memorized as kids, well, there's a whole other universe of pattern and structure just waiting for us to see it. So how on earth do you create a pattern this intricate? You might think it's some supercomputer level stuff, but the recipe is actually incredibly simple. And it all begins with a basic multiplication grid. It's really just 4 steps. First, you start with your grid. Then you multiply the coordinates, x times y. Third, and this is the absolute key, you find something called the digital root of that number. And finally, you just assign a color based on that root. That's it. The whole secret sauce is in step 3. So, what is a digital root? Okay, so the digital root is what you get when you just keep summing the digits of a number until you're down to one single digit. So, take 58. You add 5 plus 8, that gets you 13. Still 2 digits, right? So you do it again. 1 plus 3 equals 4. And there you have it. The digital root of 58 is 4. It's basically a way to boil any number, no matter how huge, down to its essential single-digit soul. So let's look at a standard multiplication table. This ought to look pretty familiar. It's predictable, it's linear, and let's be honest, it's kind of boring. This is our before picture. Now let's apply that digital root trick to every single number on that grid. And boom, this just emerges out of nowhere. It's the same math underneath. We've just looked at it through this new lens, and suddenly we see this incredible hidden structure of stripes and repeating blocks and these beautiful sweeping curves. Right, so this isn't random. That's the crucial part. There are deep mathematical rules that are governing every single pixel of this thing. Now that we know how it's made, let's start decoding these patterns. You see, this pattern has rules. The entire infinite plane is just built from one single 9x9 grid, tiled over and over again like a bathroom floor. And those bold stripes you see? They pop up at every multiple of 3. And the coolest part? Those elegant, swooping curves? They're actually the ghosts of hyperbolas, real mathematical shapes that are suddenly made visible by this whole digital root process. But we can go even deeper. What if instead of coloring by the final digit, we color based on how many times a number can be divided by 3? This view has a fancy name, a 3-adic valuation, and it shows us something amazing. The pattern is no longer just repeating, it's self-similar. You see the same structures nested inside each other, getting smaller and smaller at every scale. This is what makes it a true, honest-to-goodness fractal. Okay, so we have this beautiful, deeply structured mathematical object. And this is where our story takes a really wild turn. We're about to pivot from pure math into a whole framework for philosophy, for semantics, for language itself. You know, the person who came up with this fractal posed a fascinating challenge. They didn't just see numbers, they saw a potential language. They asked, what if each number, each color in this grid, could actually be mapped to a fundamental concept of existence? And they started with the absolute basics. The number 1, for instance, became change. The number 2, which drives so much of the pattern, became choice. And the number 0, which forms the axes that ground the entire grid, well, that became eternity. And from that tiny seed, a whole philosophical language started to grow. The ideas got more refined. Change, tied to the number 1, eventually evolved into consciousness with the symbol alpha. Choice got mapped to the number 3. And as you can see here, the system just kept expanding into a 32-part ontology where huge concepts like community and its exact opposite, separation, are all grounded in the fractal's own logic. So, if you can build a language of philosophy on this grid, could you also build an intelligence? And that brings us to the most ambitious, most out-there application for this whole thing. Using the fractal of Senezi as a blueprint for AI. The core idea here is pretty radical. You know how AI normally learns structure from scratch inside a black box we can't really see into? Well, what if? What if you built this mathematical logic directly into its architecture from the start? What if its internal wiring wasn't random, but was structured according to the rules of this very fractal? So how would it actually work? Well, you can think of it like giving every word a unique mathematical fingerprint. You'd calculate its digital root, not just in our normal base 10 system, but in several different number bases. This would create a really rich, unique signature. That signature then gives the AI a built-in sense of structure. From there, you just gently nudge the AI's attention to follow the logical patterns that are already baked into that fingerprint. The potential result? An AI whose reasoning we can actually follow because its logic is based on a structure we can see and understand from day one.
I mean, let's just pause for a second and appreciate this journey. We started with a third-grade times table. We applied one simple trick, the digital root, and we followed that thread from a beautiful picture to a philosophical language and all the way to a potential new architecture for artificial intelligence. It's pretty incredible.
And that really just leaves us with one final kind of mind-bending thought. The fractal of Senezi was hiding in plain sight, right inside the simplest math we all learn. It just makes you wonder, what other simple patterns, what other forgotten corners of basic arithmetic might be holding their own hidden universes, just waiting for someone to